there's a little bit more that's going on in these dots. And what about this dest argument here? So originally molt_store takes 3 arguments. Molt2 only takes 2 arguments. Is it okay to have the extra argument passed in? In a sense, yes. The problem is that molt2 might call some other functions and might mess with this register rdx, but we need the value dest after we get come back from molt2. So that's why the full code actually looks like this. We move rdx, that is the value of dest, into the rbx register, and then after molt2 is called, then that value in the rbx register is still there, and so we can move the result for molt2, right? The result t for molt2 can be moved into the memory that rbx points to. So you can see two things were happening here. We made a copy of rdx because rdx might be modified, but we just copied into rbx. Couldn't rbx also be modified? Well, yes and no. rbx is a preserved register, which means that when the function call returns, it's supposed to have the same value that it had before. Whereas rdx is not preserved. There's no guarantee when a function call returns that rdx will be the same. In general, the registers have different categories. Some of them are temporaries. That means when you call a function and the function comes back, the register can have any value. Except for RAX, there's no guarantees about the value compared to what it had going in. So if the caller needs the values that are currently in those registers, the caller is responsible for saving them. So another word for these kinds of registers is callee saved. RSI and RDI, the argument registers, turn out to be in this category. You set them for arguments, but there's no guarantee what they have when the function comes back. It turns out that R10, which is not used for arguments, but also is in this temporary category. Other registers, like RBX, are preserved registers. There's a guarantee that when you call a function and the function returns, that the register still has the same value that it had before. And it doesn't mean that the function that you call can't use that register, but if the function that you call wants to use that register, it's responsible for saving the old value and restoring it before returning. So that's why these are called callee saved registers. You could think of RSP as a special kind of callee saved register. After all, when you call the function and it returns, the stack is supposed to be back where it was when the function was called. The categorization of registers as preserved or temporary and so on, these are defined not by the machine, not by x86, but by operating systems, and particularly the operating system's application binary interface. The only thing that guarantees it is the C compiler. Assuming the C compiler is not broken, it will produce functions that follow these rules about temporary and preserved registers as specified by the ABI of the operating system. And for x86-64, Linux in particular, that's the categorization I've been talking about. So in that operating system and processor, RAX is a return value. We've talked about the argument values. R10 and R11 are extra temporary registers with no particular argument or return meaning. All of those are callee saved registers. RAX is a little special. It's going to change when a function call returns, but it changes in a particular way to provide the return value. The others change in unspecified ways. On the other hand, these other registers are caller saved. That means when you call a function, you can rely on these registers still having their value when you get back. There's only 4 of them that you can rely on that way that are general purpose registers. There's a couple of more. We've talked about the stack pointer. We're going to talk more about RBP as we go, but it has a similar role to RSP. So just as one more example, let's look at call incr2. So call incr2's job is to call increment, and it's going to illustrate callee saved registers again. Here's the machine code for call increment 2. And the first thing it does is that it saves RBX. That's because call increment 2 wants to use RBX. RBX is callee saved, and so that means that call increment 2, as the callee, needs to save RBX's current value if it wants to use it meanwhile. And later it wants to use RBX because it wants to save RDI. RDI is the value of the first argument, x, and that's because we want to use x after the increment. So we stash it away in RBX so it'll still be there when increment returns. Right, after increment returns, RBX can be used and combined with V2, which is the result of increment. So that's why we add RBX to REX there. Before call increment 2 returns, though, it needs to restore the callee's RBX. So that's the other half of the callee saving action on RBX. Meanwhile, call increment 2 does some other things. It makes some space on the stack for v1. It initializes v1 here, and the address of v1 is the argument to increment. So we see that we use LEA here to compute 8 bytes off of RSP, moving it into RDI, the first argument to increment.